So welcome everyone to our virtual Polygon at City. We're extremely happy today to have Ashoke Sen with us. I think we all have learned over the years a lot from Ashoke's work on string theory, and especially for my generation who was doing their PhDs at that time, we all were very grateful for Ashoke's many lectures and explanations that even as first years and second years we could follow and learn from. So Ashoke is almost the perfect speaker for this Polygon seminar. So which the polygons are meant to be, as you know, for students and postdocs. The only weakness is that he is not a London-based speaker, but in this virtual world, I think that's one advantage of COVID, I guess, that we can assume that Ashoke is in London with us as much as anyone else. So please, Ashoke.
Okay, thank you very much for the invitation. So let me start sharing. Okay, so this is the title of my talk. And so the way I'm planning to organize this talk is that first I'll give a general overview, and that will be using slides. And then I'll try to describe some explicit calculations, okay, for the results that I'll be mentioning in the overview. And those I'll try to do on the whiteboard. So here is the brief plan of the talk. So I'll first give a brief introduction to the problem. In fact, okay, this will not be very brief because this will be, in fact, at least half an hour, I would think. And then I'll describe how we solve these problems using string field theory. And then I'll end with the final remarks. Okay, and in this part, as I said, I'll try to use mostly the board so that you can see the calculations explicitly. And most of the talk will be based on these two references over here. So let me begin by describing the problem that we want to address. And so this problem, in fact, has been around with us almost since the beginning of string theory. Because you know that amplitudes in string perturbation theory are usually expressed as certain integrals over the string worldsheet variables. But these integrals often run into divergences. And the simplest example of this kind is the Venezian amplitude, okay, which was the first amplitude that was written in string theory. This is the amplitude for 4 open string tachyons. And the amplitude expressed as an integral over the worldsheet variables has a form like this. And here P1, P2, P3, and P4 are the momenta of the 4 external particles, all regarded as ingoing. Okay, so an outgoing particle will be counted as momentum minus P. And if you examine this, you see that this amplitude diverges, this integral diverges for P1 whenever 2P1 dot P2 is less than or equal to -1, or 2P2 dot P3 is less than or equal to -1. And the conventional viewpoint that one takes here is that we define the amplitude for the values of P1 dot P2 and P2 dot P3, for which this integral is well defined. Okay, and that requires 2P1 dot P2 to be larger than -1 and 2P2 dot P3 to be larger than -1. And then we analytically continue this to other kinematic regions. So what I'll describe first is a slightly different viewpoint that is provided to us by string field theory. This is different, but it will be an equivalent viewpoint, at least for this problem. But we will see that there are other problems for which the viewpoint, this viewpoint breaks down, whereas string field theory viewpoint still works. So let me say a few things about string field theory. So for the time being, it will be enough to know that string field theory is a regular quantum field theory, and it's designed so that the Fireman diagrams of this theory formally reproduce the amplitudes that we calculate using the worldsheet formalism. But the advantage in string field theory is that we have a clear physical interpretation of the divergences that we saw in the previous slide. And to see this physical interpretation, let's consider the Swinger parametrization of a propagator in a quantum field theory. So a Swinger parametrization of a propagator takes this form. You take a propagator k square plus m square inverse, and you write it as an integral of this kind. Okay, s is the proper time variable. And we will also use often this variable q, which is related to the variable s by e to the minus a, q equal to e to the minus s. And in terms of q, this integral takes this form. So in string field theory, of course, you have infinite number of particles, infinite number of fields. So there are infinite number of values of m squared. But it's useful to write a compact form of this. Okay? And that is the eigenvalue of the L0 operator. So k square plus a, the role of k square plus m square is played by the eigenvalue of the L0 operator, where L is the zero mode of the Virasoro generator. And the analog of the Swinger parametrization that we see here can be written like this. Okay, so L0 inverse is given by this integral over here. Now, the advantage of using this Swinger parametrization is that once you do that, then the momentum integrals can be done very easily. And in string theory, this parametrization also allows us to sum over all the internal states in a Feynman diagram. So at the end, we are left with the integration over this variables q. And these variables q, in fact, become the variables over which you integrate. These are the worldsheet variables, okay, after some appropriate redefinition. So in other words, the parameter q that we saw here will be related to one of these parameters q that appears in the Swinger parametrization of string field theory by an appropriate functional relationship. And viewed this way, okay, we can now identify the origin of the divergences. Okay, and one can show that all the divergences that we encountered in the worldsheet formalism can be traced to divergences in string field theory that come from the q goes to 0 limit. So because of this, we are going to try to examine the q goes to 0 limit in a little more detail. Okay, what are the kinds of divergences we encounter in this limit? So here is this identity again. L0 inverse is given as in the terms of the Swinger parameter integral. Now, if you look at this relationship, it's clear that this is an identity for states of positive L0. Okay, as long as the L0 eigenvalues are positive, then both sides are finite. Okay, and this holds identically. But if L0 is negative, then you see that the left-hand side, of course, remains perfectly finite, but the right-hand side is divergent, right? Because as q goes to 0, this blows up with a power that is faster than q inverse. And in such cases, string field theory instructs us to use the left-hand side, because from the perspective of string field theory, this is more fundamental. This is the expression for the propagator. And we got this expression because we have chosen to use the Swinger parametrization, which doesn't quite work for negative L0 states. Whereas from the worldsheet perspective, you don't know about this L0 inverse as a propagator. You only see these integrals. So if we follow this procedure that string field theory gives us, then it's easy to see that it's equivalent to analytic continuation that we saw in the worldsheet formalism when analytic continuation is available. And finally, when you consider states with L0 equal to 0, then of course both sides are divergent. Okay, so this is a genuine divergence in the theory. And from the perspective of string field theory, what it reflects is the presence of an on-shell state in the internal line of a Feynman diagram. Now, here, of course, the divergence is very much there. But in quantum field theory, we know that whenever some internal line goes on shell, then there is a physical reason behind it. And quantum field theory usually tells us how to resolve this problem. Okay, that how to get around these divergences. In the simplest cases, you use the I epsilon prescription, which will be the equivalence of analytic continuation. But often we encounter more complicated cases where just the I epsilon doesn't work. But nevertheless, quantum field theory always has an understanding of what to do with such states. Okay, it basically says that if you encounter a 1 over 0 in an internal propagator, that means that you are doing something wrong. Okay, you should analyze the system differently. And we will see examples of this. And the idea here is that then whenever you encounter divergences of this kind associated with L0 equal to 0 states in the worldsheet formalism, we'll use insights from quantum field theory to deal with these divergences. So that's the general philosophy that we are going to follow in these lectures. So what we are going to discuss today is a specific situation where analytic continuation fails, and we need to invoke string field theory to make sense of the divergences. And these involve D-instanton contribution to string amplitudes. Okay, so what I'll do now is to describe what the problems are in dealing with D-instanton contribution to string amplitudes, and then how to resolve them. So let me say a few words about what are D-instantons. So D-instantons, okay, I'll use a somewhat general definition of D-instantons. Okay. For the purpose of this talk, D-instantons will be D-branes which have Dirichlet boundary condition on all non-compact directions, and that includes the Euclidean time directions. So physically, D-instantons represent saddle points of the Euclidean path integral in string theory, and like all other saddle points, they give non-perturbative contribution to string amplitudes. And often they play an important role. For example, if you are familiar with the KKLT scenario for moduli stabilization, they are in order to stabilize the Kähler modulus of the Calabi-Yau manifold, we need D-instanton induced superpotential. And if you want to compute systematically the superpotential that is induced by D-instantons, you need to learn how to calculate amplitudes in the presence of D-instantons. Now, the problem that one faces in calculating these amplitudes is that open strings that live on the D-instanton, they do not carry any continuous momentum. And as a result, we cannot move away from the singularities by varying the external momentum. And you can see this here, that in this example, if we encounter states with k square plus m square negative, where this is divergent, we can say that we first define it for k square plus m square positive by going to a value of k where it's positive, and then analytically continue to values of k where this turns negative. But if k is strictly 0, then of course you cannot do this. Or even if k takes only integer values, you cannot do this. Analytic continuation doesn't work. And that's what happens for D-instantons. Now, often one can argue that the divergent parts, that the divergences that one finds in the presence of D-instanton, they should cancel after summing over diagrams. But the finite parts that remain after this cancellation become ambiguous, because you are really subtracting two infinities, and there is no unambiguous way to extract a finite part, okay, at least within the conventional worksheet formalism. So what we are going to do is to study this in a specific context, in the context of bosonic string theory in 2 dimensions. But the method that we will describe can be applied to any string theory. And the reason that I have focused on this particular theory is because here the answers are known from a dual matrix model. So whatever result we get from direct string theory calculation can be compared with the matrix model result to see if the results agree or not. So let me say a few words about this 2-dimensional string theory. So the worldsheet theory of this 2-dimensional string theory is a free scalar x that describes time coordinate, and a Liouville field theory with central charge 25. Okay, so the Liouville field theory has a linear dilaton background which provides the central charge 25. So total central charge adds up to 26, and that means all the anomalies are cancelled on the worldsheet. And you can really think of this as a critical string theory with a somewhat involved worldsheet theory, right? Instead of getting 26 free scalars, you have one free scalar and a Liouville field theory with central charge 25. So one advantage of this theory is that the closed string tachyon is actually a massless state of the theory. So even though we'll refer to this as a closed string tachyon, it's actually a massless state of the theory. And so the theory at least is perturbatively consistent. Okay, you can calculate amplitudes to any order in perturbation theory without running into any problem. Now, in this paper, Balthazar, Rodriguez, and Nin, they calculated actually not the perturbative amplitude. So in the earlier papers, they had computed perturbative amplitudes and compared with the dual matrix model result. But in this particular paper, they computed the D-instanton contribution. Okay, in fact, they focused in this paper on the single D-instanton contribution to 2-point function of 2-point amplitude of closed string tachyons. So one incoming closed string tachyon, one outgoing closed string tachyon, 2-point function, and they're focused on the D-instanton contribution. And as I've already told you, that this model is interesting because there is a dual matrix model description that gives the exact results. So in the next few slides, what I'm going to do is to describe some of the results that they found in their calculation. And there you will also see the kind of divergences that we encountered when we try to do these calculations. So let me start with the leading contribution. Okay, so what do you mean by leading contribution? By leading contribution, one means that it's of course an instanton contribution, right? So there is always a factor of e to the minus 1 over gs. So gs is a string coupling constant and 1 over gs is the instanton action. But the leading means that this is always common for one instanton amplitudes, but the rest of the factor should be leading in parts of in an expansion in parts of G string. And in this particular case, that happens to be ordered G string to the 0. So let me first explain the counting of parts of G string, okay, leaving aside, of course, the C to the minus 1 over GS. So the disk has, this is 2.5 product of two disk amplitudes. So the disk having Euler number 1 has a factor of GS to the minus 1. Okay, so 1 over GS. And the closed string vertex operators carry factors of GS. Okay, that's the standard normalization of closed string vertex operators. So together they give order GS to the 0. Okay, so this one-point function has no factor of GS. So each of these go as GS to the 0. And so you see that here you don't have any other power of GS. This 2 pi delta omega 1 plus omega 2, this I'll have more to say about this later. Okay, but for now, just think of this as the energy conserving delta function. This, as we'll see, doesn't quite come from this diagram, but this comes from something else. Then you have these two factors of 2 sine hyperbolic pi omega 1 and 2 sine hyperbolic pi omega 2. Omega 1 and omega 2 are the energies of the incoming and outgoing tachyons. So incoming energy I'll level by minus omega 1, outgoing energy I'll level by omega 2. So these are the one coming from the one-point function of these tachyons. And in fact, these factors can be traced to the Liouville part of the correlation function. The X part is more or less trivial. And finally, there is this normalization factor N. So the naive expression for this normalization factor is given here. So it's I. Okay, this I is common because this is in all string amplitudes. When you compute S matrix, you have a factor of I. And then it's given by the exponential of the annulus partition function. Now, why exponential of the annulus partition function? And the point is that annulus, okay, if you take an annulus without any vertex operator, then because it has Euler number 0, it goes as GS to the 0. So you can multiply this product of two disk one-point function by any number of annuli 0-point function. Okay, they don't cost factors of GS. So you really have to resum that sum, the sum over all possible insertions of the annuli, and that's this exponential of the annulus partition function. And in this two-dimensional string theory, one can explicitly calculate the annulus partition function. And we'll see more of this later, okay, how exactly this comes, but this is the expression that we have in this two-dimensional string theory.
Sorry, Ashok, this normalization factor, is it related to the tension of the D-instanton, or the mass of the D-instanton?
No, this is related to the tension of the D-instanton, 1 over G string. Okay. This is, you can say it's a one-loop correction to the tension. You can think of it that way.
I see.
Is the determinant. I mean, if you have an instanton, right, then you have a one-loop determinant, right, that multiplies the instanton amplitude. So this normalization factor is the analog of that.
Thanks.
Okay, and we'll see this more explicitly later. Okay. But from the worldsheet perspective, it's just sum over all annulus amplitudes, and that's there. And here you see that the first instance of a divergence, because this integral, you can see diverges from the t equal to infinity n. And this 2 pi t, in fact, is the Swinger parameter. Okay, this plays the role of the Swinger parameter. So this is the first instance you see that you have a divergent expression in this D-instanton amplitude. And you cannot you cannot carry out an analytic continuation because this coefficient is fixed. Right? There's no adjustable parameter in this coefficient that you can vary analytically continue.
So just to follow up, this normalization doesn't, a similar normalization wouldn't come up if I was considering some D-brane process? If I was considering, say,
that will be like the one loop correction to the D-brane mass.
So there would be such things as well, right? Yeah.
Exactly.
Okay. Okay.
Yeah, certainly. Except that this divergence is typically absent in those cases. It's D-instantons are spatial because of this zero mode problem. Okay, and that we'll see. Okay, now one point to emphasize here is that normally we don't include disconnected worldsheet, right? And the reason for not including disconnected worldsheet in an amplitude is the same as the reason why in a field theory you don't normally consider disconnected diagrams, because disconnected worldsheet typically have separate energy conserving delta function or separate energy momentum conserving delta function, and so they don't contribute at a generic for generic external energies. So naively, if you look at this amplitude, you might expect that okay, this is the same. Okay, this should have been proportional to the product delta omega 1 times delta omega 2. But the point is that D-instantons, because D-instantons have Dirichlet boundary condition on the time coordinate, the D-instanton boundary condition actually breaks time translation invariance. And as a result, individual disk amplitudes do not conserve energy. So there is no delta omega 1, delta omega 2 factor from these individual disk amplitudes. And as we will see that the energy conservation is actually restored at the very end after we integrate over the collective coordinates that describe the position of the D-instanton. And this we'll discuss in detail later. But this is just to say at this stage that because of this absence of energy conserving delta function on individual disk amplitudes, we really have to include this. Okay, this is in no way different from a connected diagram. Another point I should perhaps mention is that normally the annulus amplitude that we are summing over, right, those are like bubble diagrams, right? And normally we would say, okay, they should factor out. But here, the reason that the bubble diagrams are important is because what they measure is the relative contribution of the perturbative amplitude to instanton amplitude. And so for this, the perturbative amplitudes are not accompanied by these bubble diagrams, the instanton amplitudes are. And so it's important to include these diagrams, okay? Because when you divide by the sum of all the bubble diagrams, these diagrams don't quite get cancelled. So we really need to include this exponential of the annulus partition function, okay, this amplitude in the expression for the D-instanton amplitude. Okay, so now we go to the next order. So at the next order, there are three contributions. One is the 2-point function on the disk, okay, which I have shown here. And BRY computed this 2-point function. This computation, in fact, is quite complicated because, first of all, it has a modulus. Okay, this integral over y that you see is a modulus. So you can put one of the vertex operator at the center, but the other vertex operator, the distance from the boundary, that's a modulus. So you have to integrate over it. But more importantly, they couldn't get a closed form expression for this, for the Liouville part of this correlation function. So they have to really express this 2-point function in terms of the Liouville conformal blocks. So it also involves an integration over the Liouville momentum. Okay, so it's a complicated integral that they wrote down. But here I'm going to present the result in a compact form. So the way I have organized this is that this is the leading contribution, okay, that we saw in the previous slide, okay, product of 2 disk 1-point function. Then there is an extra factor of G string. Okay, this counting you can see as follows. Okay. So the disk, there's a 1 over G string, and each of these vertex operators carries factors of G string. So that gives you G string square over G string. So that's this net factor of G string. Okay. And then whatever is left, I'm calling this function f omega 1 omega 2. So what BRY did was to express this f as an integral, not only of this over this modulus variable y, but also over this Liouville momentum. And then they found that this integral actually diverges from the boundary of the moduli stress from the y goes to 0. So y goes to 0 limit here corresponds to keeping one of these at fixed position at the center and taking the other one to the boundary. Okay, so that is a singularity of this integrand as that happens. And then they extracted the singular part, okay, which they wrote here. Of course, you can always add finite terms here and subtract it from here. But they chose to extract the singular part like this. And then this part is now a finite integral. And they could numerically evaluate this. As I said, there is no closed form expression. It's given as integrals. So they numerically evaluated this to find this as a function of omega 1 and omega 2. But this part is what will be of interest to us, because you see that here there is divergence from the y goes to 0 end, and the exponents are independent of any external energies. So you cannot treat this divergence by any analytic continuation. So at this stage, the best we can do is to label this as some constant AF that represents this integral, and then another constant BF times omega 1 omega 2 that represents this integral. And then, of course, the finite piece is well defined. Okay, so I'll label AF as in this way. AF and BF at present are unknown constants. From the world sheet perspective, they are divergent constants.
Sorry, what is there no divergence when the two vertex operators come together?
Yeah, so when the two vertex operators come together, that's a closed string channel. So there is a divergence, but that you can do deal with by analytic continuation.
Okay.
So that's part of this F finite. So we are now focusing on only those divergences that you cannot deal with by analytic continuation.
Sorry, may I ask a question? Why in the tree level diagram there is no annulus multiplying it?
Here?
Yeah. So you said that the n appears in this
so it multiplies this. Yeah. So n is always there. See, any diagram, you can multiply by arbitrary number of annulus, right?
That's right.
Because that doesn't cost any factor of G string.
Exactly.
So that's why n is a common multiplicative factor in all the diagrams.
I thought you said that in the perturbative piece it doesn't appear or something.
Oh, in a perturbative piece, actually, you can show that it cancels out. The bubble, there's this argument that says that you divide by the sum of bubbles, right?
Right.
So the perturbative piece, you can show that it cancels out. But the D-instanton piece, it doesn't cancel out.
I see.
Because the D-instanton, you divide by the leading order bubble term, right? Which is only the closed string bubbles.
That's right. Okay, thanks.
So that's why in the perturbative piece, this part is not there. The bubble is not there. Meaning it's there, but it cancels out by the usual argument of factorization of the bubble diagrams. Yeah, I mean, if one writes out the numerator and denominator, it becomes clear that that's the way the cancellation works, right? That the bubble diagrams don't quite disappear from these.
Right. Thanks.
Okay, so next one at the same order is the product of this one-point function and annulus one-point function, okay, which I have shown here. And then, of course, there's an exchange of 1 and 2. And again, we can count power, and all of these are multiplied by the exponential of the annulus, right? Which I have not written, but you can see this n is always there. So here, this gives you 1 over G string times G string, so that's Gs to the 0. And this one, annulus gives you Gs to the 0, and then the vertex operator has a factor of Gs. So this is of order Gs. And so again, I have labeled it in this way. So this is the leading contribution over here. Then there is this factor of Gs. And then these two contributions, I'm calling G of omega 2 plus G of omega 1. So G of omega is essentially the ratio of the annulus one-point function to the disk one-point function. Right? Because if you replace this by the disk one-point function, you get back the leading contribution. So again, BRY computed G. Okay, but they could only express this as an integral over this Liouville momenta and the various moduli. And again, they found that it has divergent pieces. Okay, they extracted a divergent piece here, and the rest is finite. So here V, okay, maybe I can say the interpretation of V and X. So V goes to zero limit, okay, which is one of the sources of divergence, corresponds to the annulus becoming long. And the X goes to zero corresponds to the vertex of water approaching the boundary. Okay, those are the two kinds of divergences that we see here. And again, you can see the divergences that we see at the V goes to zero and the X goes to zero end cannot be tamed by deforming omega, right? Because there is no, the exponents do not depend on omega. So again, we do the best we can. We write G omega as a constant plus another constant times omega squared. That's this one. And then, of course, the finite piece, which is well defined. So the final factor is the product of two d square point functions and a 0-point function on a surface of Euler number -1. So this includes a disk with two holes. So here is a disk with two holes. And you can also have a torus with one hole. So there are two classes of diagrams. I have only drawn one of them. So the product of two d square point function, of course, is here. And this is the just a partition function on a surface of Euler number -1. And then you also have this replaced by torus with one hole. And here the parametrization is easy. Okay, this is the leading contribution. That's the product of these two. And this is, of course, just a constant. This doesn't depend on any external energy. So I write this as G string times C. Okay, G string because this is Euler number -1. So G string to the minus Euler number. That's the factor of G string. So you can now add up these results and get the total result for the 2-point function to order GS. And here it is. Okay, this is the total result to order GS. And now if you write F, G, and C, okay, C of course is just a constant, okay, and it's in fact in general divergent. By the same reason, okay, various degenerations cause divergence. So you write F and G in terms of its finite piece and the divergent pieces. And if you do that, you get an expression like this. So you see that at this stage, these are unknown constants. And the result depends on these two independent combinations, this combination over here and this combination over here. Now, as I said, the actual result for this is known from the matrix model. Okay, matrix model gives the exact result, which you can carry out an expansion and you can read out the instanton contribution. So you can compare the matrix model result, okay, which I'll write down in a few minutes. And what BRY did in their original paper was that they of course couldn't compute F and G analytically. So they plotted this as a function of omega-1 and omega-2. In fact, as a function of, because of this, there is a function of one variable, omega-1. So they took the function of omega-1 that you get from this, treated these as arbitrary parameters, and then they found the best fit values of these two constants. Okay, so they determined the values of these two combinations. So I'm going to give the result, but in a few minutes. Okay, after we discuss some generalization of this. Okay, are there any questions up to this point? Now it turns out that using the same functions, we can actually get expressions for the endpoint function of closed string tachyon. Again, up to the same order, GS times e to the -1 over GS. So here, the leading contribution comes from the product of n disk one-point functions. And you can easily read out what it is, right? The same normalization constant n, exponential of the annulus, the same e to the -1 over GS. This is the energy conserving delta function. And the only difference is that here you have a product of n such factors instead of just two factors. And this is just a rewriting of that, okay, this leading contribution. So at next order in G-string expansion, there are three types of diagrams. First, you have n-2 disk one-point function and one disk two-point function. Then n-1 disk one-point function and one annulus one-point function. And n disk one-point function and the 0-point function on surface of order number -1. And the important point that I want to emphasize here is that the pieces which are involved are exactly the same pieces that we have already analyzed. The disk 2-point function, annulus 1-point function, and the 0-point function on surface of Euler number -1. Now you might ask, what about n-3 disk 1-point function and 1 disk 3-point function? Of course, these diagrams are very much present, but their contribution is of order gs squared. And the way to see it is that these, of course, give gs to the 0, each of these, n-3 disk 1-point function. And a disk 3-point function gets a 1 over gs from the disk and 3 factors of gs from the 3 closed string vertex operator. So that's gs squared. So they don't contribute to order gs. So it's easy to convince yourself that to order gs, these are the only 3 contributions. And the result that we get by this analysis is given here. You can easily recognize that this is coming from the first amplitude, okay, after some overall possible ways to distribute these external closed string vertex operators into the disks, this 2-point function and the disk 1-point function. That's this sum. This one is coming from here, and the last term is coming from here. And now we are again going to use these expressions for f and g that we wrote earlier. Okay. The finite pieces are well defined, and you have these constants af, bf, ag, and bg that are entering the expressions for f and g. Okay, so the idea is that we will now substitute this in this expression over here. So if you do that, then this is the result that we get. Okay, that this is, I just substituted the expressions for f and g in terms of the finite piece and the divergent piece. Okay. So the finite pieces are given here, okay, and the divergent pieces are organized here. And what you notice here, okay, is that unlike in the previous case, where only one combination of AF, AG, and C appeared, the n equal to 2 case, right? There, if you remember, it was AF plus 2AG plus C. Now, if you look at this expression, not for a particular value of n, but collectively for all values of n, okay, then you see that individually we can determine AF, AG, and C by comparing this with the known result from the matrix model for different values of n. So here now I have written down the result for the same thing, okay, but computed from the matrix model. Okay. And this is here, you can see that it's a nice compact expression. Okay. So you can basically numerically compare these expressions, this expression over here with this expression over here, okay, and find the best fit values of these individual constants. Okay. This always appears in this combination. So in this Bg minus Bf by 2, this is the combination that enters the S matrix element. Okay, so here I have again written the same identity. And then BRY just compared this, okay, these two sides. Okay, this is still not a published result, but by comparing this, we can see the leading term, okay, of course, can be compared analytically. Okay. The leading term comparison gives you n equal to minus 1 over 8 pi square. Okay. And then the subleading term, okay, they can only be compared numerically because of the lack of knowledge of these analytically. Okay, so these are evaluated numerically, and they get the best fit values of these constants to be what is given here. And the errors in each of these is about 0.01 in their determination. So the question that you are interested in asking is it possible to determine these from string field theory? Okay, because we said that in string field theory, you should in principle be able to make sense of the divergences that we encountered in the worldsheet formalism. So can we do this? And can we actually fix all these constants in string field theory? So I'm now going to give a brief overview of what we do in string field theory. And then I'll try to state the results and then switch to the board to do some explicit calculations, okay, to show exactly how these calculations are done. So what is the strategy that we follow in string field theory? So here is the strategy. So we first take the worldsheet expression for an amplitude, and the finite parts, of course, are well defined, so you don't have to worry about those. So we focus on the divergent part that are associated with the open string degeneration. Okay. For example, in the normalization factor, we have a divergence from any t goes to infinity n. Right? In the calculation of the this 2-point function, we have divergence from y goes to 0 n. And in the annulus 1-point function, we have divergences from the v goes to 0 n and x goes to 0 n. Then we are going to make appropriate change of variables from these t, y, v, x, etc. to the string field theory Schwinger parameters, which you had labeled by q1, q2, etc. And this change of variables is provided by string field theory. Okay, how to make this change of variable. Okay, that's where string field theory is used. Okay, the explicit form of string field theory. Then these divergences that you see here, okay, now they become divergences as the q goes to 0 n from one or more of the qi's. So then the prescription is that whenever we encounter a divergent integral like this, we interpret this as coming from a negative L0 state, right? Because these kinds of integrals come from integral dq q to the L0 minus 1. So when you encounter divergent integrals like this, you simply replace it by 1 over L0. So here this we interpret this as L0 equal to minus beta state. So you just replace this by minus 1 over beta. So this is what string field theory prescribes to us to do. Okay, that a divergent power of divergent integrals like this, you have to replace by minus 1 over beta. So the subtle points are associated with the beta equal to 0 divergences. Okay, those are the logarithmic divergences. And as we discussed, those are associated with the L0 equal to 0 states. Okay, and they need special care. So this is what I said, the divergent integrals of this form, the logarithmic divergence. These can be traced to the 0 modes. And these cannot be treated using Fireman diagrams, right? Because whenever you have, in this case, remember that there is no momentum, continuous momentum that you can adjust. So if you encounter in the internal line of a propagator, a 0 mode, that means that you are doing something wrong, because you know the 0 modes cannot be treated using Fireman diagrams. So the first step in this analysis will be to explicitly subtract out these divergences, these terms. Okay, that after you have changed variables to q, whenever you encounter integrals like integral 0 to 1 dq q inverse, you replace this by 0. So this corresponds to unintegrating them in the path integral. Okay, this means that actual path in the path integral, whatever variable you integrated to produce this 1 over zeros, okay, we are unintegrating them. Okay, we don't want to do those integrals using Fireman diagrams. So once you do that, then the next step will be to find the physical origin of these modes. Why are you getting the 0 modes in the first place? And after you have identified the physical origin of these modes, then you have to treat them accordingly. Okay? And there is no uniform prescription for this. Okay, you have to really look at a mode, identify why it's coming, okay, and then treat them accordingly. For example, we will see that some of these modes come from collective modes. Okay? They basically are there because the D-instanton can be translated in the Euclidean directions, Euclidean time directions, sometimes Euclidean space directions. So those are 0 modes, okay? And as we said, those 0 mode integrals have to be done at the end, okay? And they produce a momentum conserving delta function at the end. Okay? So those integrals have to be done explicitly at the end. We'll also see that some of the 0 modes arise because of the breakdown of the gauge choice. In particular, the 0 modes that we encounter in the gauge sector reflect that the Fourier determinant actually is developing 0 eigenvalue. And that means that your gauge fixing is not correct. Right? Because if you have done a proper gauge fixing, then the gauge determinant should have a non-zero, should be non-zero. So in that case, you know that your gauge fixing is breaking down. So you go back to your original gauge invariant path integral and try to either do new kinds of gauge fixing or try to evaluate that original gauge invariant path integral explicitly. So this is the way we are going to treat the L0 equal to 0 modes. Okay. First analyze their origin and then treat them accordingly.
So this removal by hand, it seems like, at least naively, it might be there might be some ambiguity in that. I guess what you're saying.
Not after you change variable to q. Right? If you use the original variables y, x, etc., then of course there's an ambiguity. But string field theory gives an unambiguous prescription of how Q's are related to the Y's, X's, and so on. Once you have changed variables to Q, right, then these Q's are really giving the swinger parameters. And removing this basically means that you are removing precisely the contribution from the propagator of that particular massless mode and nothing else. And that's what corresponds to unintegrating these modes in the path integral.
So what singles out these Qs? I mean, why can't I come up with some other variables?
A string field theory gives the correct relation. Then once you have fixed a string field, the version of string field theory, okay. Now here I should say that the particular version of string field theory, there are many versions of string field theory. In fact, there are continuous families of string field theories, okay, which you can show are all related by field definition. Right? So the physical results would be the same in all of those. So once you have fixed a particular version of string field theory, this change of variables is unambiguous. So the idea that you fix a particular version of string field theory, make this change of variables, carry out this procedure, then what you will find is the individual expressions will depend on the particular string field theory you have used. But
okay,
at the
so
end,
then I should ask why is this version of string field theory singled out?
Yeah. So the point is that at the end, the physical results shouldn't matter on what version of string field theory you have used. Right? So this is in fact a strong consistency check on the calculation.
Okay.
That individual Fireman diagram contributions will depend on how you have, which particular version of string field theory you have chosen. But at the end, when you add up all the results, then you will find that the final results should be independent of those parameters. And this can be used as a check to make sure that you have not done something wrong in your calculation.
Okay, thanks.
Right? But this is a very useful constraint that, I mean, in a sense, you can say that it makes string field theory ambiguous. On the other hand, it gives a strong constraint on the strong check on the results that the final results should be independent of this parameter, this choice of string field theory. Is that okay?
Yes, thank you.
Okay, so I'll maybe show some examples at the end, okay, of how these cancellations work. Okay, so here are now the results from string field theory. Okay, and I'll try to then explicitly show how some of these results come. Okay. So here the C is question mark because C has not been computed from first principle. Okay. And the reason is that it's just more complicated, right? Because it requires this calculating the partition function on a disk with 2 holes, right, or torus with 1 hole, right? That's like doing a genus 2 calculation. Okay, it's the projection of a genus 2 Riemann surface, and that calculation is more difficult. But in principle, there's nothing stopping us to do the calculation for C using the same procedure. Okay. So the others have been computed from string field theory, and here are the results. And here are the results of the matrix model, right, which I have already quoted. And you can see that the results all match except this one. Now, right now, it's not clear what is the origin of this mismatch. The simplest explanation of that is that I have made a mistake in the calculation. Okay. But I'll show you some, the different pieces that contribute to AG, right? And we'll see that they are reasonably non-trivial, and at the end, they all add up to give something that is independent of the parameters of string field theory. Okay. So at least it's not obviously wrong, but at present, we don't know what is the origin of this discrepancy. But everything else matches nicely, including this N. This is, of course, analytical on both sides. And the numerical values are that you see here, right? AF and 2BG minus BF. Okay, they match nicely with the analytical results from the string field theory. And about C, I should just say that even though there is no direct computation of C in string field theory, there are indirect arguments which show that it should vanish. Okay, this is not a full-fledged string field theory calculation, but there are indirect arguments that one can give showing that the C should vanish in string field theory. Okay, so I think this is the end of the overview. So now I'm going to switch to the whiteboard. Are there any questions on this?
Yeah, I had a quick question. So the fact that there's no direct computation of C is just that, is it technical or is more than a technical issue?
No, it's just technical. I mean, okay. It's technical because, okay, let me show you this diagram. Okay. It's just that BRY didn't do the analog of this calculation. They did all the other calculations, but not this one. If you give the expression for this from the Liouville theory, right, then you can follow exactly the same principle to tame the divergences and get a finite answer. Right? You just don't know the original integrand. Yeah. So that's the reason why this has not been calculated. And in principle, as you go to higher order, right, you will encounter more and more divergences of this kind. And in each case, you can just follow exactly the same principle to extract finite result out of those. Okay, so the procedure that string field theory gives is completely well defined. Now it's another question whether they agree with the matrix model or not, right? But at least as far as string field theory is concerned, there is a completely well defined set of procedure that is laid out of how to extract the finite pieces. Okay, so let me now switch to the board. I think I probably have 10 minutes before the break, right? So I'll start.
Yes, that's right. Yeah.
I'll start on this and then we'll continue afterwards.
Great.
Okay, so what we are going to do is to calculate n. Okay. So the first thing is to let's try to calculate n. Okay, let's see how this goes. Okay. And this, in a sense, is technically simplest because you don't need much detail about string field theory. Simpler, but conceptually, more subtle. Okay, and it in fact basically involves all the subtleties that we'll encounter eventually. Okay. So naive expression that we wrote down is this: I times exponential of a, okay, where a is the anomalous partition function. Okay. And I'll write down the expression for a in a general string theory instead of focusing on the two-dimensional string theory from the beginning. Okay. So this is integral 0 to infinity dt over 2t trace e to the minus 2 pi t L0. Okay. So this I can also write as integral okay. So this trace is taken over all states. This is over all states in the CFT. In the matter goes CFT. But projected by B0, C0. So B0 and C0 are the zero modes of the B and C ghosts on the worldsheet. Okay. And this projection operator basically comes from the fact that annulus has B and C zero modes. Okay. So to define the annulus partition function, you use the projection operator B0, C0. Okay. So this means that we sum over states with B0 on the state equal to 0. Okay, so that's what this sum runs over. So the sum over I means sum over all bosonic states. Okay. HIB is the L0 eigenvalue of the bosonic states, and this is the sum over fermionic states. HIF is the L0 eigenvalue of the fermionic state. Okay. Now you may wonder how come they are in a bosonic string theory there are fermionic states. Okay. And the point is that this, of course, includes also the ghost modes. Okay. So there are indeed fermionic states also in bosonic string theory. Okay, and those are the ghost states. Okay, from the point of view of string field theory, these will be the ghosts of the Fourier-Popov after you do Fourier-Popov quantization. So you remember in the case of two-dimensional string theory, you had this factor of 2 pi t minus 1. Okay, so you clearly see this minus 1. Okay, that comes from the host nodes. So we'll focus on the two. We'll do the two-dimensional string theory in a few minutes afterwards. So let me write the expression for A again. So divergences come from t equal to infinity n due to HIB less than or equal to 0 and HJF less than or equal to 0 states. There is in fact no divergence from t goes to 0 end. Okay, this is the in fact ultraviolet end from the open string perspective, okay, in a consistent string theory. Which basically means that these, as t goes to 0, these two terms cancel. Okay. And when you say this, there's no divergence in a consistent string theory, this basically means the following: okay, that because of this open closed string duality, you can interpret the t goes to 0 limit as a divergence in a closed string channel. And you can show that from the closed string perspective, as long as there are no closed string tachyons in the spectrum, okay, there is no divergence as t goes to 0. As t goes to 0, these two terms must cancel. Okay. And that's what happens, for example, in two-dimensional string theory or superstring theories. So if we look at this integral, okay, so if HIB and HJF, if these are positive, then we can write we can express A, we get, okay, let me, then we can actually do this integral analytically, and A is given by half log product over J HJF divided by product over I HIB. Okay, this you can easily check that this integral over here basically gives you this. So this means that e to the A, which is ratio of product HJF over product over I HIB, okay, can be written as an integral now. Okay, so let me write this integral: product over I dBi over square root of 2 pi product over J. Okay, here I'm using the fact that the eigenvalues in the fermionic sector always come in pairs, so you can write this as pair. So this product runs over half the values that we encounter, that you see here, because you have doubled the number of variables. Okay. And then you have an exponential of minus half sum over I HIB times BI square minus, sorry, plus sum over J HJF F tilde J FJ. Okay. So this is just an identity, right? I have just rewritten this as an integral. Okay. And these factors of square root of 2 pi, etc., are going to be important because you are trying to get this e to the A without any normalization ambiguity. So this is an identity, and this is what we are going to use. So the idea is that this formula, of course, is valid when these eigenvalues are all positive. But we are going to take this as a definition of e to the A, even when these eigenvalues are negative or 0. So we're going to take this as a definition of e to the a. And then we'll argue that whenever there is a divergence, okay, which means whenever one of the h's vanish, okay, negative h's are not a problem because they can be defined using steepest descent contours. Okay. Vanishing h's are the problematic cases. Okay. We'll argue that whenever the h's vanish, okay, it is because of a physical reasoning. Okay. And so the steps that we'll be following is as follows. So let me just say the steps and then I'll stop for this part of the lecture. So the first thing we'll do is to interpret this integral that we have seen as a result of gauge fixing of a gauge invariant path integral. Then we'll show that the divergences that we get from the zero modes of the fermions can be traced to the breakdown of gauge choice. Okay, because these fermions will come from the ghost sector. And if you get a zero mode in the ghost sector, that means that the gauge choice that you have made is wrong. Right? That because the Faddeev-Popov determinant is getting a zero. So then we'll repair it by going back to the original gauge invariant path integral and using that instead of using this gauge fixed path integral. We'll also show that the divergence that we encountered from the HIB equal to zero modes, those correspond to collective modes. And their integration has to be done separately, and that will recover the energy conserving delta function at the end. And we will see by following this, we should be able to extract a unambiguous finite answer for this integral over here. Okay, even when some of the eigenvalues are 0 and negative. So maybe I stop here now and then we'll continue in half an hour.
Yeah, that sounds great. So maybe we can all unmute ourselves and thank Ashoke for the first part of his seminar. And if there are questions, please go ahead.
Ashok, I had a question about this last point. So
yes,
this Fischler-Susskind mechanism, which you just described in the perturbative string theory, in world sheet theory, how does that how is that manifested in the string field theory? I mean, here you're talking about some open string field theory.
Yes. So Fischler-Susskind mechanism, okay, there are various kinds, but in string field theory, it's exactly what you do in normal quantum field theory, right? That you find that the effective action maybe has developed a tadpole, right? A one-point function in the effective action. And the way you repair it by looking at the full effective action and finding a new minimum.
Right, but here is there some infinite set of, I mean, the full effective action means what? Like there's some infinite sum or something like that?
Yeah, you can take it as an effective, not just an effective action. By effective action, I meant the 1pi effective action, right? You have all the external string states, right? Take the 1pi effective action by integrating out the quantum, right? And then you can extremize it. Okay, that's what you do normally in the usual Fischler-Susskind closed string sector. Here the problems are somewhat different, right? It's called Fischler-Susskind, but it's not quite the Fischler-Susskind kind.
That's right. Yeah.
It's Fischler-Susskind only in the sense that there is the cancellation between two divergences.
That's right.
But it's not exactly what you call Fischler-Susskind.
But it's supposed to. So in this case, I understand. But more broadly, is that how it will work in closed string field theory? That you can sort of remove tadpoles by shifting the vacuum, and is that consistent in the string field?
Yeah, if you can find a minimum of the effective action, then it's consistent.
Right.
But of course, there's a guarantee that you'll find a minimum.
I see.
Right. So it's not that you can always solve a tadpole problem this way, right? But in just like a normal quantum field theory, right? Right. You have an effective action that may not have a minimum, right? In which case it's not a consistent. There is a consistent vacuum. So from the perspective of string field theory, there is really no difference between what happens in normal quantum field theories. But in this case, as I said, the problems are different because here, there is a continuous momentum, right? So here, most of the problems are coming because this is really an integration over a discrete set of variables. Right? So if you have an L0 equal to 0 state, it's not that it's a massless state, it's actually a 0 mode. So there's no I epsilon that you can use to regulate this. You really have to learn to integrate over the zero modes explicitly.
So another question I had was, in the very first part of your introduction, you sort of focused on one mode in the closed string field theory and then looked at the integral over it. Right?
Okay, let me go back.
I mean, just when discussing like you say that divergences should be thought of as 1 over L0.
Yes.
Right? Now, in the full string field theory, I'm sorry, it's a technical question, but in the full string field theory, you would be presumably integrating over the sum of all modes or something like that.
Sum overall. Yes.
Sum overall modes. And,
yes.
and there's no issue with sort of swapping the sum over all modes and the integral. This is
no, because what happens, because what happens is that these sum over all modes, right, is actually exponentially convergent, because one can show a string field theory vortices have an exponential of minus m squared.
I see.
And the number of states grow as exponential of m. Right? So even though there are infinite number of states, right, because of this, because the vortex has exponential of minus m squared,
I see.
It's an absolutely convergent sum. Right? So there is a problem of swapping the integrals first and the sum. And I mean, you can trace it down to basically the fact that the OP in a conformal field theory has finite radius of convergence. Right? And that basically it follows from there. That is, this exponential suppression of the string field theory vortex is a reflection of that fact, that there is a finite radius of convergence in OP in conformal field theory.
Do we have other questions for Ashok that want to be recorded, or shall I pause the recording for now and then we can chat more informally? Okay. Perhaps I'll pause it then.
Okay, so should I start?
Yeah, why don't we start with the second part then, please, Ashok?
Okay, thank you. Okay, so let me remind you that this is where we were, right? We had this expression for e to the a, and now we have expressed this as an integral. And our goal will be to try to interpret this, first of all, as a gauge fixed path integral of a gauge invariant string field theory, and then try to go back to the gauge invariant form. Now, here first, let me just mention one more thing, that we are talking about string field theory. But if you look at the open strings on the D-brain, right? Open strings on D-instanton, they do not carry continuous momentum, that you have already seen. Which means that the open string field theory that you're talking about here is really a zero-dimensional field theory. Namely, the path integral is over a discrete set of variables and not over fields. Okay, so this path integral I should really put in a quote, because this is really ordinary integral. And that's what you see here, right? I mean, what you see here is just a set of integration over a discrete set of modes. Now, in the situation of interest, okay, which is in two-dimensional bosonic string theory, and in fact, superstring theory, for example, and many other string theories, it's even better. Okay, so let's look at this now. So we have e to the a. Okay, let me write the expression for a. That's good enough. So a is integral dt over 2t trace e to the minus 2 pi t L0. Right? This trace is taken over states that are inherited by B0, which are also sometimes called the Siegel-Gauge states. So this in the 2D string theory is given by integral dt over 2t e to the 2 pi t minus 1. And just for reason that I'm going to explain in a few minutes, let me write this as e to the 2 pi t plus 1 minus 2. Okay, basically we'll argue that there are two bosonic modes and two fermionic modes. But what we see by comparing with this, okay, this and this, okay, is that the contribution from all the L0 positive states have cancelled. Contribution from L0 greater than 0 states cancel. And what you are left with is a finite set of modes with L0 less than or equal to 0. Okay. So the situation in fact is even better. Okay. Not only that we have the path integral is replaced by an integration over a discrete set of variables, okay, but you in fact have integration over only a finite set of variables. Okay, not an infinite set of variables. So I'll write down explicitly the states that contribute in this two-dimensional string theory. So Siegel-Gauge states. Okay, in this case, Siegel-Gauge basically just means that B0 is equal to 0 states. In 2D string theory with L0 less than or equal to 0. Maybe I should say open string states, right? Because we are looking at not the closed string states, but open string states on the D-instanton. In D-instantons into the string theory. Okay. So these are C1 on the vacuum, then C0 on the vacuum, sorry, not C0 on the vacuum, I made a mistake, because we are writing now only the Siegel-Gauge states. So C1 alpha minus 1 on the vacuum. Okay. These are bosonic states, okay, because the statistics of the state are inversely correlated to the ghost number. Okay, so they have odd ghost number, that means these are bosonic states. Okay, this is a tachyon, for example. This is the massless bosonic mode that transcends the D-instanton. Alpha is the X oscillator, the oscillator associated with the time coordinate. Okay. And the fermionic states, okay, are 0 and C1, C minus 1, C1, 0. Okay. So these have L0 equal to 0. Okay. This has L0 equal to 0. And these are the L0 equal to minus 1. Minus 1. Okay. So total contribution then is 2 pi t. This is coming from the L0 equal to minus 1 state. Plus 1, right? That's coming from here. And minus 2, which is coming from here. Okay, that's what we see as e to the a. This is the BRY answer for the annulus partition function. Okay, so we have a clear interpretation of where this partition function is coming from, which states are contributed. Okay, now we have to give some more details on open string field theory. Okay, fortunately, we will not need too much at this stage because we only need the free open string field theory, right? Because you are working at a quadratic level. For the annulus partition function, we only need a quadratic part of the open string field theory. So first, let me define in the worldsheet theory. So in the worldsheet theory, we define Gauss number as follows. We assign C and C bar as Gauss number -1, B and B bar as Gauss number +1, and all the matter fields like X and Liouville as Gauss number 0. And then we denote by phi n r as basis of states of Gauss number n. So for L0 less than or equal to 0 states, the whole list is finite. The full list is finite. So let me list out all the states. C1 on the vacuum, 0, then C-1, C1 on the vacuum, C1 alpha -1 on the vacuum, and then the others are just C0 acting on this. So the first 4 satisfy the Siegel gauge condition, B0 on this equal to 0. The others don't.
And all the Liouville states would be L0 bigger than.
Yeah. Well, basically what happens is that on the instanton, the open string states come only from okay. So the closed string states, of course, contain a lot of Liouville excitations, but on the instanton, if you look at what are the primaries, right, that live on the instanton, it's the ground state of the Liouville and the ground state and the alpha -1 on 0 state of the matter. And then you, of course, apply all the Virasoro generators and the C's. Right? So the Liouville sector, for example, L-2 of Liouville acting on the vacuum will contribute. But at this level, L-1 on the Liouville, right, is 0 because of it's a SL2R invariant vacuum. So there is no, you cannot construct any excitation in front of the Liouville at for the L0 less than or equal to 0 state. And L0 larger than or equal to 0 states get contribution from Liouville, but they all cancel. Okay, so you don't have to worry about integrals over those. And this, in fact, as I said, is not special to this. I mean, it's a feature of many string theory, like superstring theory, for example, also has this feature. Right? There is cancellation between the Neveu-Schwarz and Ramon sector for the L0 positive states. And even if they don't cancel, okay, you can do those integrals explicitly and get a finite result. Okay, even if you cannot do it analytically, you can evaluate it numerically. It's a finite integral, right? Because you are just doing the bosonic integrals and harmonic integrals and dividing. And as long as the number of degrees of freedom is the same, you are guaranteed to get a finite result. But in this case, we really have, I mean, a finite number of states to integrate over, finite number of modes. Okay, so far I have not said anything about string field theory, right? This is just a worldsheet theory. So now let me say something about string field theory. So the classical open string field is an arbitrary state in the worldsheet theory of Gauss number 1. What this means is the following, that let's suppose that we expand a state, arbitrary state of Gauss number 1 in a basis. Okay, so you can expand it in this way. Phi 1r is by definition the basis of states of Gauss number 1. So you can expand it in this basis. And these psi r's are the dynamical degrees of freedom. So the path integral, okay, or the integral in this case, have to be performed over this variable psi r. That's the classical open string degrees of freedom. So if we go back to this, the ghost number 1 states in this list are here, right? This is ghost number 1. Then this one is ghost number 1. And this one is ghost number 1. Okay, of these are single gauge states. This is out of single gauge state. Okay, but these are the ghost number 1 states. The classical string field theory in this case will contain 3 independent components: the coefficient of this, the coefficient of this, and the coefficient of this. And the quadratic part of the string field theory action has a form of, let me call this S, gauge invariant action, psi QB psi. Okay. So which QB is the BRST operator in the worldsheet theory. Which basically means that you substitute this expansion in this expression over here, and you get some function of the psi r's, and that's by definition is a classical action. Okay, you define path integral weighted by e to the minus s, the Euclidean path integral. This theory also has gauge invariance. So the gauge transformation parameter of the classical string field theory are encoded in an open string state of ghost number 1, ghost number 0. Which basically means that if we take this arbitrary state of ghost number 0 and expand it out in a basis, then these are the gauge transformation parameters. And the infinitesimal, I should have said infinitesimal. Okay, we are always talking about infinitesimal parameters. And the gauge transformation law is delta psi as QB on theta. So if you expand theta in this basis, and if you expand psi in this basis, then by comparing the two sides, the coefficients of each basis state on the two sides, you can read out how the individual components of psi transform under theta. Okay? That's what we mean by gauge transformation law is given by this.
Sorry, Ashok, so like if I had a normal D-brane, then there would also be the gauge symmetry. Is this gauge symmetry talking about the SUN gauge symmetry that we would, the analog of that?
Yes,
or?
yes, it is an analog. So the SUN gauge symmetry will be part of this. Okay. Appropriate choice of theta will generate the SUN gauge transformations, right? For a single D-brane, right? It's a U1, yes. And this theta includes the U1 gauge transformation. Yes.
So this is not to do with the diffeomorphism invariance, for example. That
no, because that's a closed string sector. That's a closed string.
Exactly.
Yeah. Exactly. So the open. I mean, here you are talking about open string gauge invariance because you are really doing open string path integral. Mm-hmm. Those strings are not going to play any role because any degeneration involving closed strings, you know that we can deal with by analytic contribution, right? So you just focus on the open string sector and how to carry out the path integral over the open strings.
But formally, there would be some BRST operator, which was really a sum of all these things.
Exactly. Yeah, both closed and open string.
Yeah.
Exactly. Okay, any other question? So now, based on this, I can now define a gauge invariant path integral as follows. Integral product over R. This integral runs over all the classical string field. Divided by integral product over U d theta U. Okay, that's the gauge invariant path integral that we have. Okay, this is the way we normally write down a gauge invariant path integral. This normalization here is completely arbitrary, okay, fixed arbitrarily. At the end, it makes no difference if you multiply this by any arbitrary constant. Okay, and it will hopefully become clear as we proceed. So if we go back, we had identified the classical gauge string field components, right? Those are the three of these. The coefficients of these are the classical string field components. And we can also identify the gauge transformation parameter. It's basically, this is the only ghost number 0 state in this, right? So there is only one gauge transformation parameter that multiplies 0 in this particular problem. Okay, even though I have written that in general. Now, I'll skip some of the technical details, but let me just make state the result. Okay? That if we formally fix Siegel gauge, if we formally fix Siegel gauge, then, and using Fourier procedure, then I can be shown to reduce to the integral that we had. This should be sum over j. This is sum over I. This is sum over j. Okay. So the way it comes, let me just indicate briefly that first of all, Siegel gauge fixing in this case means, in this two-dimensional context, Siegel gauge fixing will basically set the coefficient of this to 0. Okay, that's because this is not the B0 acting on this is non-zero, so the coefficient of this will be set to 0. So you basically use the parameter theta to set one of these C0 to 0. So in that case, okay, in the Siegel gauge, first of all, what happens is that this QB, which appeared in the kinetic term, this QB, okay, that just becomes C0 L0. Okay. So this kinetic operator just reduces to the L0 eigenvalue. Okay, and that's what explains why this coefficient is HIB. This is just an L0 eigenvalue, right? So the kinetic operator just becomes minus half HIB BI square. This one comes from the Fourier-Popov ghost. If you calculate the determinant, okay, of the Fourier-Popov ghost that you get by changing variable from theta to the corresponding size, okay, that's the determinant you have to calculate. That you can show is again proportional to the L0 eigenvalue, okay, and that gives this HGF. So this is the ghost part. So these are coming from the Fourier-Popov ghosts in this language. So these are.
Can I?
Yes, go ahead, please.
So in this BRST operator that we just talked about, that's the BRST operator for the U1 gauge symmetry or the The analog
So
of
this
the
is the
U1.
BRST operator for the diffeomorphism. No, this is a worldsheet BRST operator always refers to a diffeomorphism. BRST operator. Is a standard BRST current.
Then I think I misunderstood. So that BRST operator is not the one for this gauge symmetry that
No.
d theta.
No. This is a worldsheet BRST operator.
Yes, I see. Yeah,
but
yeah.
the gauge symmetry from the space-time language, right? This gauge symmetry translates to the open string gauge invariance. So QB has the usual structure of Cn minus n, for example, right? QB has the structure Cn L minus n, and then there is also the CC beta, right? So that's the same BRST operator, but it's the open string sector only.
Yes. And this is unrelated to the gauge, the U1 gauge, the theta gauge.
Yeah, it is not unrelated. That when you translate, so this BRST operator, as you can see, appears in the space-time translation invariance, right? This QB theta.
Okay.
So maybe I can just explain it in the following way. Suppose you had a D-brane. Okay, not a D-instanton, but there's a momentum.
Yes.
If you have a momentum carrying state, then the gauge transformation parameter, there will be a theta of k multiplying the k vacuum, right? Instead of vacuum, you'll have the state of momentum k, right? And you have an integral ddk. See? When QB acts on this, it produces a state proportional to k mu alpha mu minus 1 on k, right? So this means that this is, and then there is C1.
So this means longitudinally.
That this is changing the coefficient of the, if you write the string field also as integral ddk, say a mu of k alpha mu minus 1 C1 on k, right? Then this is giving delta a mu is equal to k mu times the theta of k, right? Times theta of k. So this is precisely the momentum space version of delta a mu of x as del mu of theta x, and up to these factors of I. So that's the way the gauge invariance, the usual open string, the U1 gauge invariance comes out of this.
Thanks.
Is that okay? Okay. So let me go back here. So I have said this. So this is the idea is, so this gauge invariant path integral, okay, after gauge fixing becomes this. And you can see that this quantity over here, okay, as this quantity over here, okay, is precisely 2 pi to the power nb by 2 times e to the a. Okay. We had written down the expression for e to the a. Okay. That is exactly like this, except that each b had a factor of b integral db over square root of 2 pi. Okay. So that is missing. So this is 2 pi to the nb by 2 times e to the a. Okay. So what is nb? Nb here is the number of bosonic modes in the Siegel gauge. So the idea now is that if we have HIF equal to 0, right? That's the problem we are facing, right? If you have 0 modes, that means some of the H's vanish. Okay. That means that the ghost determinant is vanishing because this is the ghost term. So the problem that we are facing with the HF equal to 0 states is because you have done the wrong gauge fixing, we are getting a vanishing ghost determinant. So the idea is that we will identify e to the a, not with this, okay, this over 2 pi to the n by 2, but because this is formally equal to this, e to the a will be taken to be 1 over 2 pi to the n by 2 times this. Okay, that's the way you are going to interpret e to the a. So let me write that, and then maybe it will become clearer. So we shall define to the a as Is this clear? So let me repeat again. So in this form, right, in the form that we had originally had, okay, if you focus now on the specific problem that we have in two-dimensional string theory, there are two bosonic modes, two fermionic modes in the single gauge. What we are saying is that that is the wrong expression to use, because that is obtained actually from this by doing wrong gauge fixing. So the correct interpretation of e to the a is this integral, which is a gauge unfixed version. So that means there are more bosonic modes. There are in fact 3 bosonic modes here, because you don't impose a single gauge condition. You don't have any ghosts because you have not gauge fixed. Instead, you divide by the volume of the gauge. Okay, and that's what we need to do. Okay, so this, you are now going to interpret this as the expression for e to the a. So in the present problem, we have psi. Okay, there are 3 components. So psi is psi 0, C1 on the vacuum. And then you have psi 1, C0 on the vacuum. This is out of single gauge state, plus some other variable phi, C1 alpha minus 1 on vacuum. Okay. Theta was theta times the vacuum, right? The ghost number, there is only single ghost number 0 state. And NB is 2. Okay, because NB is the number of bosonic modes in the single gauge. That was 2, right? Because that's coming from the psi 0 and psi 1. So you have now an expression for e to the a that you have to handle. And we can evaluate S, which is half psi QB psi. Okay, and substitute this expression for psi, this expansion, and you can easily verify that this is given by minus half psi 0 square minus psi 1 square. Okay. So the idea is that we will not try to substitute this here and try to make sense of this integral. Is this clear? Are there questions?
Phi has disappeared.
Phi?
Yeah.
Yeah, phi has disappeared because it's a collective mode, right? We don't expect the action to depend on phi. Okay, so this remains as a 0 mode, okay? And you have to try to make sense of this. How to do the integral over phi, right? So we have not resolved all problems, right? We have gotten rid of the fermionic 0 modes, right? The ghost problem, okay, but we still have to integrate over phi and theta, right? And we'll see how to do this. So this then leads to the following expression for e to the a. We have 1 over 2 pi because it had this 2 pi to the nb by 2. And then in the numerator, you have integral d psi 0, d psi 1, d phi, e to the power half psi 0 square plus psi 1 square over integral d theta. Now the psi 0 and psi 1 integral can be done by using steepest descent contour. Okay, we'll see the justification of this later. Which is along the imaginary axis. And in fact, the fact that psi 1 is integrated along the imaginary axis, that is a somewhat fake statement, because what one can show that when you do this expansion, okay, the correct way of doing this expansion in the correct way to maintain a reality condition is you should have had an I in the first place in front of psi 1, okay, because that only then this psi 1 will be a real variable. Okay, this follows from the reality condition on the string field. But anyway, it doesn't matter at the end because this I will eventually cancel, okay, as you'll see. So you keep it like this to integrate along the steepest descent contour. And so this gives e to the a as minus 1 over root 2. Now these integrals are just Gaussian integrals. Okay, the minus sign comes because of the 2i, right? Because each of these, because you are rotating the contour along the imaginary axis, you will get a factor of I, and integral d phi over integral d theta.
So the overall sign is unambiguous. You might imagine rotating in opposite orientations, the I and minus.
So the overall sign, in fact, is fixed by unitarity. Okay, that depends on the choice of contour.
Yeah.
Right? Original contour, and then we'll see later, right, that is actually fixed by unitarity. So right now, let's not worry about the overall sign. Okay, we keep it ambiguous at this stage. Okay, so let me write this again. So you have e to the a as minus 1 over root 2 times integral d phi over integral d theta. So we have seen already that phi is related to the D-instanton position along x naught, okay, which we call phi tilde. Okay, so we'll see that phi is not exactly phi tilde, okay, but phi is related to phi tilde, and theta is related to the rigid u1 on the D-instanton. Okay, so what is the rigid u1? Okay. That if we take any open string from the D-instanton to another D-brane, it could be a second D-instanton, okay, or some other D-brane. Okay. Then this acquires a phase e to the I theta tilde under D1, under the rigid U1. Right? This symmetry always exists. Okay, this basically says that there is every D-brane has a U1, right, under which an open string that stretches from that D-brane to another D-brane is charged. So that parameter is what we are calling theta tilde, and this theta can be shown to be related to theta tilde. Okay, and in fact we saw in if you work with not a D-instanton but a normal D-brane, then it was clear from this this example over here, right, that this theta that we have here, right, is really the gauge transformation parameter, the U1 gauge transformation parameter on the D-brane. But now we have to do a little more work. Okay, you have to find the actual relation between phi and phi tilde. Okay, so that the work I'll not do, I'll give the results. So the actual relation between phi and phi tilde can be found by comparing phi coupling computed from string field theory to the expected coupling of the phi tilde. Phi tilde coupling is known because phi tilde is at the position of the D-instanton, right? So you know how things will change as you move the D-instanton, how the various correlation functions change as you move the D-instanton. Similarly, the theta tilde relation. So this is the theta tilde relation. can be found by comparing the gauge, the open string gauge transformation law, okay, and here you have to go to the nonlinear level. You cannot just work with the linearized gauge transformation, but you know what the nonlinear transformations are in the open string field theory. Open string field theory gauge transformation laws with theta tilde transformation. Okay. And the result is that phi is phi tilde over pi root 2 times G open, and theta is I theta tilde by G open, where G open is the open string coupling constant. In this case, in fact, we don't need it, where it cancels. Okay. But in general, it's proportional to square root of G string, and you can find a constant of proportionality. Okay. This is a coupling constant that appears in the open string field theory. So now we are ready to calculate e to the a. So e to the a was minus 1 over root 2 integral d phi over integral d theta. So now I'm going to write in terms of phi tilde and theta tilde. So minus 1 over root 2. Okay. So phi tilde was phi over pi root 2 G open. Okay. So 1 over pi root 2 G open. This comes from the phi tilde relation. So now it becomes integral d phi tilde. And here now instead of integral d theta, we will write I over G open times integral d theta tilde. So this gives you this I and minus and this I over, this is 2 pi integral d phi tilde over d theta tilde. Okay, that's what we arrive at. This is the expression for e to the a. Now you remember that this e to the a was multiplying this other amplitudes, right? The product of these amplitudes and so on. And this phi tilde integral, okay, the integration over the collective mode is supposed to be done at the very end. Okay, this is the as you said, the integration over the collective modes is done at the end of all other calculations. So this integral d phi tilde will generate eventually, after you put in the closed string 1-point functions, 2 pi delta omega y factor. So this we have already separated out. This was not part of n, right? We wrote it separately from n. So this is not part of n. Okay, so as far as the calculation of the normalization constant is concerned, you can forget about integral d phi tilde because this is going to produce this factor, which is written separately. Integral d theta tilde is 2 pi. Why? Because theta tilde has period 2 pi. You can go back and check the theta tilde is defined with a normalization where the phase that the open string picks up is equal to the I theta tilde. Right? So this clearly shows that theta tilde is periodic with period 2 pi. So this integral gives you 2 pi. So then e to the a is I over 4 pi square. So we are almost there, okay, but not quite. So maybe now I'll just switch to the slides again, okay, for a few minutes, and then we'll come back to the blackboard. Okay, so what is left? Okay, so we have got e to the a, okay, but a little bit more work is needed. And the work that is needed is related to what is called the multiplier factor. So what we have computed is a leading contribution from the steepest descent contour around the instanton. But now you have to figure out how does the steepest descent contour around the instanton actually fit inside the full contour along which the path integral is to be performed. Right? Who tells you that you have to integrate over the steepest descent contour? So you have to first understand the actual integration contour. And so to do this, we look at the open string tachyonic mode. Okay, psi naught. This is the relevant field over here. Psi 1, as I said, is that integration is really real. Okay, we got this factor of I just because we have chosen that we didn't expand it correctly, right? But that cancels with the extra factor of I from theta. So the psi 0, which is the tachyonic mode, okay, it's known that the potential for psi 0 has this shape. Okay? So it has a maximum at psi 0 equal to 0. That is the D-instanton. Okay, so this is the D-instanton. It has a minimum, okay, at some value. This, in fact, you can show is a perturbative vacuum. Okay, that the tachyon potential vanishes here. And it's also known from the study of tachyon potential that the potential is unbounded from below on the left-hand side. Okay, as psi 0 goes to minus infinity. So this means that when you actually carry out the integration over psi 0, then we cannot do the integral along the real axis. Okay, that's an ill-defined integral because the potential goes to minus infinity as psi 0 goes to minus infinity. So the weight factor in the path integral e to the minus b will actually approach infinity as psi 0 goes to minus infinity. Okay, so that makes the path integral ill-defined. So it turns out the correct choice. Okay, on the other hand, okay, on the right hand side, on this side, you have to pass through this point, right? Because this is a perturbative vacuum. Okay. So it better be that the integration contour that you have chosen is such that it captures a full perturbative contribution. Okay. So that means that it must include the full steepest descent contour around the perturbative vacuum, okay, which is a positive real axis. Okay. That is the perturbative contribution to the closed string amplitude. The matrix model, of course, contains both perturbative as well as the instanton contribution. Okay. So based on this, one can argue that the actual integration contour has to be taken like this. Okay. Now, here we could have either taken it like this, okay, or you could have taken it like this, okay, coming from top and going like this. Okay. And that will make a difference in the change sign of the contribution from the instanton. Okay, this part, of course, will remain the same. That's a perturbative contribution. That will change the sign of the contribution from the instanton, either this one or that one. Okay. And here, the choice of sign is taken in such a way, okay, that this theory, okay, I should have said that because the integration is about a complex contour, you can check that the theory is not unitary. Okay. But by even if the theory is not unitary, okay, consistency demands that we should make sure that you lose probability. Okay? Because if you lose probability, you can interpret this as saying that there are some states that you have not accounted for. Okay? And the reason that you are finding apparent violation of unitarity is because the probability is leaking into those states. Okay? But you shouldn't get back a probability that is larger than 1. Okay? Then there is no way to explain this. And indeed, for this particular problem, it is possible to show that there is a nice interpretation of this lack of unitarity. Okay, and that is essentially that the closed strings are making transition into something called rolling tachyon states. So that's from the physical consideration. We know that the sign of the imaginary part is fixed. Okay, you get an imaginary part. Okay? So S matrix is not unitary, but nevertheless, it should be such that you get you have a loss of probability, okay? And that fixes the sign. Okay, that chooses the integration contour to be like this. But what it translates to in what you are doing earlier, okay, is the statement that this is only half of the steepest descent contour. Okay, the full steepest descent contour about the integral instanton would have gone like this. Right? You are doing the integral along the imaginary axis because that's we are just exploring the region around the origin. Okay? So the full steepest descent contour goes like this. But what this is showing is that we are supposed to include only half of the steepest descent contour in the contribution to the amplitude. So that fixes the normalization to be I times e to the a times half. Okay, that's because you have this half of this. And if you put together the expression for a and everything else, you get this minus 1 over 8 pi square, which is precisely what the matrix model gives you. Okay, so that basically finishes the calculation of n. Are there questions? Okay, so I think I have about 12 minutes. So let me try to explain the calculation of the disk two-point function. Okay, or how to do the divergent part of the disk two-point function. So disk two-point function. Okay. So this is a disk two-point function of two closed strings, right? Two-point function of two closed strings. Okay. So let me draw the Fireman diagrams in string field theory. Okay, so the Fireman diagrams that are relevant are of this kind. So I'll explain this. So in my notation, the black lines will be closed strings, external closed strings, and the red line will be the open strings. So this is one of the Fireman diagrams that contribute to two-point function, okay, on the disk. Then you have just a contact term. Okay. We have just the two-point contact interaction. And then we have another diagram, which is somewhat subtle. Which I'm going to include separately. That's this psi1 exchange contribution. So the point is that the original worldsheet expression matches onto the Siegel gauge fixed path integral. So that takes into account open strings which are in the Siegel gauge. Okay, so the original, so this part can be read out from the original worldsheet expression. But psi1 exchange cannot be read out from the original worldsheet expression. This has to be included separately. Okay, and we'll see how exactly this is done. So let's get to calculating this. Okay, how to calculate this. So this requires, so this diagram. Okay, so if we call this A, B, and C. Okay. So A requires this vertex, right? One open, one closed, one open vertex. Okay. And you can see that for our purpose, we can take this to be on shell, right? This is the external state. So this we can take to be on shell. Okay. But this we need off shell information. Okay, and that's where these extra parameters that I talked about in string field theory comes in. So this requires off shell information. So that's what we have to specify. Okay, so open closed interaction vortex. On the disk or equivalently upper half plane, right? We'll work in the upper half plane. In fact, that's easier. So on the upper half plane, we'll insert the closed string vertex operator I. You can always do this by SL2C. In fact, because you have only one closed and one open string, you can fix the positions at any arbitrary point that you like. So this I'll put at I. And the open string vertex operator I'll put at 0. Okay. So it's this two-point function that will describe the amplitude involving one external open string, one external closed string. But because the open strings are off shell, okay, you have to specify the which coordinate system in which you insert this open string. So we'll insert the O in some coordinate system. So W in general can be taken to be an arbitrary function of Z. So this is the ambiguity that comes in string field theory. But we'll make a particularly simple choice. We'll take f of Z to be lambda times Z, where lambda is some constant. Lambda is some arbitrary constant. Now let's look at this diagram. So how do you construct this diagram? So rule for computing this diagram. Okay, so here I am using various facts from string field theory, which I'm not going to prove, but I'll say how one goes about computing this diagram. Okay, and as you will see that ultimately all that it involves are some conformal maps, okay, to compute this diagram. So what one can show, okay, and this is a general feature, one can show that this computing this diagram means that we glue two copies of the upper half plane. Okay, why two copies? Because you have one upper half plane associated with this vertex and another upper half plane associated with this vertex. Okay, so let's call the coordinate here z, and for this the coordinate here z prime, and we use the relation using the relation w prime equal to q, sorry, minus q, okay, where w is the coordinate system at the open string vertex, right? This that what I have chosen here, okay, and our simple choice is lambda z, and so similarly w prime is lambda z prime. This is q, it's probably not very visible, and q is that Schwinger parameter for the propagator, okay, for this red propagator, that open string propagator that you see, that's the Schwinger parameter for this propagator, right? So essentially what you are saying is that this what string field theory tells us is that the result of computing this diagram is essentially to integrate over to get a two-point function on the disk, right? Now two-point closed string function on the disk, okay? And the disk, that the particular disk is obtained by this swing procedure. Okay? So let's see how this works. Okay, so this, if you write this as lambda z times lambda z prime equal to minus q. Okay? So this tells us that the punctures, the vertex operators, are at z equal to I. The closed string vertex operator, this closed string vertex operator are z equal to I and z prime equal to I. Okay? But using this language, it translates to z equal to I times q over lambda square. So in a sense, what you are saying is that this diagram that you see, this Fireman diagram, this basically translates to a two-point function on the disk, one closed string vertex operator I, another closed string vertex operator I times q over lambda square, and then the q is integrated from the range 0 to 1, right? Because that's the Schwinger parameterization. Now let's compare with the BRY calculation. Okay, so BRY parameterization, how did they parameterize? So BRY parameterization of the vertex operators was that one vertex operator was placed at I, the other one is IY. Okay, remember the variable y that we had? Right? This is the way they had introduced this variable. One vertex operator I, one at IY on the upper half plane. So if we now compare these two pictures, we see that y can be identified with q over lambda square, right? So this gives a relationship between y and q that we are looking for. Okay? And once you have done that, then you just follow the procedure that I gave. So as 0 less than this range translates to 0 less than or equal to y less than or equal to 1 over lambda square. And this means that the other diagram, okay, this diagram, must cover the rest of the range of y, right? By definition, okay? Because the two diagrams together should cover the whole range. So this covers 1 over lambda square less than or equal to y less than or equal to 1. Okay, so that's the way string field theory makes contact to the worksheet expression. Okay, that this diagram covers this range and this diagram covers this range. Okay, so let me translate it to numbers now. Okay, and then I'm going to stop. So remember the divergent part of f. So divergent part of f had this form that it had half integral 0 to 1 dy and then y to the minus 2 plus 2 omega 1 omega 2 y inverse. Okay. So what you are going to do is to split this y integral into two parts. One is 0 to 1 over lambda square plus integral lambda to the minus 2 to 1 of okay, just why did you split it this way? Because that's the way the two diagrams work, right? This diagram is covering the range of y from 0 to 1 over lambda square. The other diagram is covering the rest of the range. Now for this integral, we change variable from y to q because this contains a divergent piece, right? So we write here y is equal to q over lambda square, right? That's what we found here, the relationship between y and q. And once you do that, this becomes half integral 0 to 1 dq lambda square q to the minus 2 plus 2 omega 1 omega 2 q inverse, q inverse plus half integral 1 over lambda square to 1 y to the minus 2 plus 2 omega 1 omega 2 y inverse. Okay, so this is an elementary integral, right? This you can easily do, right? So this gives you half times this integral is lambda square minus 1 plus 2 omega 1 omega 2 log lambda square. Okay. In this integral, you see this is integral dq q to the minus 2. Okay, so the rules of string field theory tells us that this should be replaced by half times lambda square times minus 1, right? Because it's q to the minus 2 means that L0 equal to minus 1 state. So this is a half lambda square times minus 1 plus this is integral dq q inverse. So that's a 0 mode propagating. We are supposed to remove this, so that's 0. So after adding these two, we get a finite result, which is minus half plus omega 1 omega 2 log lambda square. Okay. And now if you remember that we have parameterized this by AF plus BF omega 1 omega 2. Okay. So by comparing this, we get AF equal to minus half and BF is equal to log lambda square. Okay, so that's the string field theory answer for these coefficients. Okay. And you see that AF is independent of lambda, BF does depend on lambda, but that combination which appears in the S matrix, that BF minus BG by 2 or BG minus BF by 2, that you can show the lambda dependence cancels out. Okay, and then you got this minus log 4 for that. So I think my time is up, so I'm going to stop. So let me just do one more thing. Oops, let me just do one more thing in this slide. I just want to show the result for G that comes, the AG, right? Because I had promised you that I'll show you the various components of AG. Okay. So I'll not try to explain this, okay, because that will take too long. Okay. But basically the point is that the AG gets contribution from many pieces. Okay. Here, lambda tilde is one of those parameters that enter string field theory, just like lambda was. H of beta is a whole function that enters the formulation of string field theory. And individual contributions depend on all these parameters. But after we add all of these, you see that all these parameter dependencies cancel. And you get this nice answer H equal to -half, which is consistent with the fact that the final physical quantities shouldn't depend on what version of string field theory I've used, even though the intermediate stages can depend on what version of string field theory I've used. Okay, so I'll just put up my final remarks and then I'll stop. Thank you.
Oh, okay. Thank you, Ashoke. Let's maybe unmute ourselves and thank Ashoke for this really beautiful lectures. Are there questions? So I had a simple question, which was, you kind of picked this in this last bit. You picked this gauge where lambda was introduced. So you the Q was equal to lambda z or something like that. Is that?
Yes. Okay.
Yeah.
Go back to the whiteboard. Yeah.
So,
it's not really a gauge, right? This choice, this one you meant.
Yeah.
Yeah. So this is a version. Which version of string field theory are you using?
Yes, that's right.
Yeah.
So, why? I mean, suppose I picked a nonlinear function. So
yeah, it's just that if you pick a nonlinear function,
yeah,
then what happens is that this it's still true that when you make this identification, you get a disk 2-point function, but the relationship between the coordinates of the new disk and these z's become very complicated. Right? In fact, you have to get it by solving a differential equation.
Yes.
So because of this, it's easier if you choose this relation between w and z as SL2R functions. You can make an arbitrary SL2R transformation and pick that function. That still makes things tractable. But if you take a general nonlinear function, then what would happen is that you can still do it, and it is guaranteed from the consistency of string field theory. The final result will be independent of what function you have chosen. But the intermediate results will depend on that function.
But can you actually carry out the calculation, or is that?
I think if you, unless you pick a very complicated function, you can't do the calculation.
I mean, let's pick z squared or something, you know.
Okay, in Wheaton, well, no, we don't want z squared. I mean, we want it to start linear in z.
Oh, I see. Because you have to.
Yeah, it has to have a good Taylor series expansion. You have to start linear in z, and then you can add powers.
Okay.
So Wheaton vortex, for example, uses a complicated function, right? It's not a simple function like this. And you could, okay, Wheaton vortex, of course, is a pure open string vortex, right? But that's just an analog of this. You could choose analog of Wheaton vortex for this case, open closed vortex, and there are various choices that you can make. And for certain class of choices, you can do the calculation in principle, and you can verify that you get exactly the same result. Here, in fact, I didn't say one thing which is an important point, that if you go in the previous one, right, we had one more diagram. Okay, this diagram, I didn't talk about this. And the reason is that this vortex actually is 0 for this particular choice of coordinate system. If you choose like w equal to lambda z, you can show that this vortex can become 0. Right? So this diagram didn't contribute. But if you take a more general SL2R vortex, okay, don't take an arbitrary nonlinear vortex, but suppose you choose an arbitrary SL2R function here. Here you take w to be an arbitrary SL2R function of z. Then what you can show is that the other diagram doesn't cancel. But this relation between q and y also becomes complicated. And at the end, the two effects cancel. Okay, this you can explicitly verify. That the final result is independent of what, at least within the SL2R class of functions, you can explicitly check that the results cancel.
That's very nice.
And as I said, I mean, it's guaranteed from the internal consistency of string field theory that the result should cancel. Although doing the explicit calculation becomes difficult if you choose an arbitrary function here.
Mm-hmm. Okay.
Right? So similarly, the calculation of AG that I described, right, that was also done by using this SL2R class of functions, because there you can do everything explicitly. Okay, and see, if you want to go beyond this SL2R class, then even to find analog of this relationship between Q's and Y's, you have to get it as a solution to a differential equation. Right? There's no simple algebraic relation between Q and Y anymore.
What order is that differential equation?
Basically, you have to solve the appropriate period equation that you have to imagine that you are getting an annulus out of doing two vortices of a sphere. Then you have to figure out the period of the annulus, right, in terms of the gluing parameters. And that involves integrating this the one form and equating. So you do that calculation from the sphere viewpoint, right, showing up the sphere, and you do a calculation separately for the annulus, and then you compare these. And that becomes a complicated process, even though in principle it's a well-defined procedure. So this cancellation that I described for the G, for example, right, this one, okay, this was all done in the within the SL2R class, right? But even that there is a lot of freedom, right? You can see there's a whole function worth of freedom in choosing these interaction vortices, and at the end everything cancels.
That's very beautiful.
Yeah, except that this answer doesn't agree with the matrix model result, right? But the point is that because it's such a, I mean, fine-tuned cancellation, right? It's hard to imagine that any of one of these answers is wrong, because that's going to change other factors. I mean, this cancellation will have to rework out again.
So likely you're just missing some extra contribution or something.
Yeah, it's likely that there is some extra contribution that is being missed, and that's somehow independent of these parameters.
Yeah.
That's some kind of universal contribution that doesn't depend on which version of string field theory you are using.
Any other questions? Maybe I'll stop recording now.
Okay.
Let's thank Ashoke once again for the very nice seminar.